Alright, hello world. I am back. Last time we did 41. Last time we did 41. So if you had phi and psi defined like this, then the sum of these is 2 to the n psi n. And the second part of 41 looks like it's sort of alternating. So alternating sum of the same thing, and you get this term. So I was going to look at 42 and 43. We actually did 43.1 as well last time because I noticed right away that we had a product. You got a product of two infinite series here, and you've got an infinite series here, and there's also factorials involved. So it was like really clearly just an application of 34's identity. All right, so yeah, 42. In 42, we're trying to show, it looks like these, first of all, you can see we've got binomial coefficient in front of them again. It's basically the same thing we just did in 41, except that phi 0 is being replaced with this function. Phi 1 is this 2 minus n squared business, yada yada. Wonder if I could, well, nah, because we're supposed to plug in x. So at 0, you're left with just a0. At 1, everything after this will die off, so you'll have a0 plus a1. Anyway, I'm pretty sure we can just apply 41 to both of these, and the answers should just pop out. 42 looks like also the right hand side has a 2 to the n. It's like sort of screaming. This is apparently psi of n right there. And then 43, I'll just write it down up here. 43 is the same thing but alternating. This time you're supposed to get 0 or possibly 8. All right, so we'll see if I can figure that out. In both of these cases, what would be nice is if, because we started with a function in 41, it has to look like this. It has to be a1x, a2, x times x minus 1, etc. But I guess it is finite, right? No, it's not finite, but when you plug in a number, it only takes the first n terms. So like you take phi of 3, you'll get, you know, it'll involve a0 through a3 is what I'm saying. Because after that, you have a term. So when you plug in an integer, it cancels out from some point on. You get a finite sum. And as you can see, this is kind of like a permutation. So like, it's like a falling factorial that stops after k terms. So if you're on like the vth term, it's x factorial over x minus v factorial, I want to say. Yeah, that's right. We can write that down if you want. A v x factorial over x minus v factorial is what the next term is. But this is, in general, it's an infinite series for this function. But whenever you plug in a, you know, an integer, or should probably say a natural number, you get a finite sum. All right, so at the moment, all I need to do is make this function match up with these coefficients. Like, make a0 be n squared. Like I want phi of 0 to equal this, and I want phi of 1. In general, I want phi of an integer to equal this term, 2 times the integer minus n squared. So I mean, I can see that that determines of course it determines a0. It determines all of them, but I'm just trying to see how I can show like is that even possible? I wonder if it's enough to just say that, like if it's obvious that I can just say that. This is a square. Huh. Yeah, wait a minute. Does this only involve like the first? It can only involve the first couple terms, right? It's a quadratic, which means it terminates. It's going to terminate here. So I could just like you could expand this, and just set the coefficients equal, and that's that. And then for all the higher orders, so like a3 and higher equals 0. A0, of course, is n squared. But other than that, these two, you know, they have to satisfy. I wasn't sure if there's a super fast way to do it. You know, other than the extra algebra of just expanding it and seeing what you get. All right. Well, if we had 2x minus n squared, and we set it equal to a0 plus a1x plus a2xx minus 1, right? This will give you the three equations that we would need for a constant and the two, for the coefficients in front of these three variables. So 4x squared, I guess that, well, yeah, it tells us a2, right? It has to be a 4, and then a1 is going to sort of correct for that. But yeah, 4x squared minus 4xn, 4nx I should have said, plus n squared. So those are a0, those are a2, and then we can sort of sort out what a1 has to be to... so on the right hand side, we have a2 x squared, and then in front of x we have a1. It looks like minus a2, right? Yeah, a2x gets put over there and there's a minus sign, so it's a1 minus a2, and then finally a0. So this is the only part that is equal to negative 4n. But we know that a2 is 4. So you're looking at a1 minus a2 equals negative 4n, where this is a 4. So a1 is 4 minus 4n, or 4 times 1 minus n. So a1 is 4 times 1 minus n, like that. So those are the three coefficients that will guarantee our phi of x equals 2x minus n squared. Well, I should say k, phi of k, because this is an integer. But anyway, that's good for phi. And the last thing I just want to check is that psi of n actually gives you n. Psi is also a very specific form. I think a0 is the same. Yeah, it's a0 plus a1 over 2, a2 over 2 squared, etc. I think. Oh, no, it's also got the factors. Sorry. X times x minus 1, etc. So this one's like x factorial Anyway, this one's like x factorial over x minus v factorial, just like above. So it's the same as phi, but with an extra power of 2 in the denominator in the coefficients. But if we plug in n, of course, using these same coefficients, of course, we're getting n squared 4 times 1 minus n, like this is 4, well, it's really a 2 now, right? Because it's all divided by 2. 1 minus n, like that. And then the third and last coefficient is a2 is a 4. So we're getting 4 over 4 times, and we plug in n. I think that's it, 1, 2. So there's only two factors there from our falling factorial business. So if we see what this works out to be, we've got a minus 2n squared there, but then I have another 1n squared over here. So it looks like it's going to work out. 2n times this, so it's 2n minus 2n squared, and then this is just n times. So these cancel, and it looks like you're getting n. And that's it. That's the proof of probably both 42 and 43. But at the end of 42, we just confirmed that psi of n will give you that n if you choose, appropriate AIs, so that the left-hand side matches up with 41s. So I think we're done by 41. And then 43, same business on the left-hand side, we just did that. But on the right-hand side, we might want to see that phi of n. Oh, it's not phi of n though. It's on 41, the right-hand side is supposed to be alternating. Like when you do the alternating business. So for 43, the right-hand side would be -1. I realize you can't see it, but it's this, there it is, up top here. When you do the alternating business, you get -1 to the n, n factorial. Most of those an's are 0, all except the first 3. So that's what's happening there. -1 to the n, a to the n factorial. So, of course, it equals 0 for any n larger than 2. We're supposed to check 2. It'll give us something interesting. And then for 0, well, like for n equals 0 and 1, for n equals 0, you only get this one term, right? If n equals 0, you get nothing. You get 0. If n equals 1, you get n squared minus n. If n equals 1, this is 1 times 1. Oh yeah, you don't get n squared, you get 1 squared. Right. Okay, so n equals 1, you get 1 minus 1. So yeah, equals 0 for both n equals 0 and 1 as well. For 2, we could write down what you get, confirm that you get 8. Yeah, we could write it down up to here, right? And confirm. Or we could just use this formula. So you're supposed to get -1 to the 2, a2, 2 factorial is just 2 times, what's a2 again? N squared, I believe. Lost track of where I wrote it. Way up here. a2 is 4. Okay, so 4 times 2 is 8. Yeah, that's it. 8. So that's it for 42 and 43. And that ends this first business. That ends section 2. So we can move on to differentiation. But I think I might call it a day there. Have a very short session on today's stream. Extremely short. All right. Have a good day, everyone.